Hello guys, welcome back. My name is Lichtron and welcome to my video channel and my website at www.drilling-academy.com, the place for drilling gurus where you will find a heap of good stuff about drilling, equipment, rig and tools operation. Welcome to equipment and principles explanations. As continuation of the PDM mud motor structural components, as promised today I'd like to present you keynotes of directional drilling operation with PDM mud motor. If you are a directional driller, it's the basic stuff. However, it should give you some important concept of drilling with a mud motor if you are not a directional driller. There are some jargons used in the video. If you are unclear what they mean, please visit the former video about PDM mud motor structural components for more explanations. First off, let's examine the relations of load configuration and geometry versus the output and the speed of a mud motor. The load configuration of a mud motor is simply put as a form of fraction as 1, 2, or 3, 4, or 7, 8. So the lower numbers like 1, 2, or 3, 4 are referred to as low load configuration, while higher numbers such as 7, 8, or 9, 10 are referred to as high load configuration. And what do they mean? They mean that low configuration lobes will produce low torque and high RPM and highest efficiency of the mud motor. Vice versa, the high load configuration will produce high torque. However, the RPM speed and the efficiency of the mud motor are quite low. And the lobe stage or lobe geometry of the mud motor is understood as one spiral lap along the rib over the axis of the rotor. For example, in this rotor here, we start from this yellow dot here, we go along this rib, go down, follow the profile up to here, come back to the same position along the axis of the mud motor, of the rotor. So this is one slice. So this rotor has one slice in the same length. In the same length here, after this rotor, we start from this point, we follow this rib, we come down, we come back up on here. We don't end up on the same point on this axis, but is in this same example here is only half a spiral lap. So in this example, this rotor has only half slice. And what does it mean? It means that the more slices are, the higher the speed is. And the next step is picking up and making up the motor onto the BHA. For this process, the first thing we do is we make sure that we record the fishing diagram of the mud motor, and we check the float valve and ensure it's installed at the correct position and direction on the mud motor. This is the top step of the mud motor. This is where you install the float valve on the mud motor and ensure that it's pointing downward so that you can pump through. And the next step is to check and set the AKO or the bend angle setting at the desired value. Every mud motor is shipped to rig at a set bend angle. Ensure that this set bend angle, this is the mark of the set bend angle, ensure it meets the requirement for the directional drilling application. Reset it if required. And the next step is checking and measuring the bearing gap. The bearing gap is a gap between the shoulder of the drive stop and the bit box, this gap here. How to measure it, how to check it, we will examine it in the next slide. And next step is to make up the MWD tools. MWD tools, this is the MWD tool, and this is the bit. Make them up onto the mud motor. Usually the good practice is to make up the MWD tool onto the mud motor first, so that you can achieve a certain length on the BHA, and it's easier to make up the bit onto the motor at that time, because with that considerable length you can reduce the level of misalignment and you can make up the bit onto the motor easier. Misalignment may cause you misleading in the torque reading. For example, if the motor is hung like this, and while the bit is sit in the bit breaker straight like this, you have this misalignment here. When you place the rig tongue on the bit box of the motor and another rig tongue here on the shoulder of the bit, and you torque up, the torque reading will show you the right torque reading as what you desire, but however you still have this misalignment. The gap is caused by the misalignment. You can check with a piece of paper. Try to insert the paper into this gap here. If it goes through, meaning you still have the gap caused by misalignment, break the bit out, redo the whole makeup here, ensure you have no gap. You know what you have, what consequence you have when you have a gap between the bit and the motor. You will lose a bit lately when you run downhole. And the next step is scribing the mud motor high side tool face and the MWD high side. This mark here on the MWD tool is called the high side of the MWD, and this mark here right at the IKO bend stop where the bend angle is set is called the high side tool face of the mud motor. You measure the distance between these two lines. They don't always end up as straight on the same line like this. They may end up, for example, this is the high side tool face of the mud motor of the MWD, and this is the high side tool face of the mud motor. So you have a distance between them. Measure this distance and work out the tool face offset and ensure that it's checked, it's entered into the system correctly, so that your entire directional drilling work lately is not junked. And the last step for making up the BHA is surface test the motor, which is simply put the motor with the bit into the rotary table and pump through the motor at low or moderate flow to watch the motor performance, like rotation and any abnormal vibration or shocking from the motor or not. And then you run the motor downhole. On the first stand of drill pipe made up onto the BHA, you perform the shallow hole test. This is the shallow hole test, sorry. The shallow hole test here, it means you pump through the whole BHA at a moderate flow, and you get all the readings from the MWD and LWD tools, ensure that the whole system is functioning correctly. Then you drill out the screw track and come on down on the bottom and drill it. Drilling with mud motor is all about sliding and rotating in combination. A good directional driller will have a sliding and rotating plan in his hand at all time, and he has to slide and rotate in combination through both the curve sections and the tension section to achieve the desired well path. Somebody may think that drilling through tension section is all about rotating, but that's misleading, because formation always has what we call formation effect. It may push you to the left, push you to the right, up or down. So then you have to do sliding to correct for the formation effect. Therefore, in tension, you still sometimes have to do sliding. And while sliding and rotating, the directional driller has to monitor all the other drilling parameters such as weight of bit, torque, reactive torque, differential pressure, and very important is he has to line up and get the correct TFO. TFO means tool face orientation of the motor for sliding. There is a very close relationship between reactive torque and TFO. Alright, when you come down on the bottom, under the effect of the reactive torque from formation, your tool face could be changed, and it is changed over times. Therefore, you have to make correction. You may have to pick up off bottom, line up the TFO and come down top bottom, and you wait for the tool face offset, the orientation to update as a dot on the MWD LWD screen in the doghouse. So the data transmission rate plays a key role in here. If it's fast enough, you get the update instantly. If it's too low, then you may have to wait for even half an hour or 45 minutes to get an update from the tool face orientation. Therefore, the patience is required a lot from both directional rulers and company men. Some company men often go after the directional ruler and ask them why it takes so long time for sliding or for orientating. But what they need to do to understand is the transmission rate from the tool down up to surface may cause delay, and the reactive torque is playing against the desired tool face. So therefore, patience is required. Sometimes it takes hours to get the correct tool face for sliding. And remember, even just 1 or 2 meters of sliding in the wrong TFO may take you 7 to 8 meters sliding in the correct tool face orientation for the correction. Therefore, don't hurry. Don't be squeezy and hustle in getting the correct tool face. Give some time. Give it time as it needs. And while sliding and rotating, we call the name is steering. The directional ruler will take a survey quite often, as often as he needs, because he needs to achieve the correct build-up rate, the desired build-up rate over the patch diameter. He has to follow the well path, the planned well path. And sometimes the tool send up some misinformation or some wrong survey data, he has to take the chest shot, and if he has any doubt about the performance of the tool, he has to take the chest shot, and then he make projection ahead, and in his projection, if he estimated he can't achieve the build effect that is required, he may have to trip the motor out to change another angle setting on the AKO. And sliding is only pumping through the string. You pump down here, and the bit is rotated by the rotor. The string is kept static. So rotate, and the bit RPM, the bit speed RPM equals the flow rate you are pumping through times the revolution per gallon pump. While rotating, you rotate the real string with the top right on the surface, while you're pumping through the string with your flow rate. So the bit is rotated quite fast. It equals the string RPM plus the GPM, which is the flow rate you are pumping, times the revolution per gallon. This is the formula for working out the bit speed with rotating. And in this picture here, we examine the steps of measuring the bearing gap, which is an important step in running the mud motor. A bearing gap is defined as the gap between the shoulder of the drive sub and the bit box. So first you hang the motor aloft on the top drive, you measure this distance, you have D1, then you sit the motor down on the floor or slip, and this bit box here is pushed back inside the drive sub a little bit, and you measure the same gap, you get D2 value, you minus them D1 from D2, and you get the bearing gap, and this bearing gap has to fall within an operational range. If it's out of range, the motor will have to be sent back to town for redress. And another key thing with running mud motor is differential pressure. Differential pressure, what is it? Here we examine it. First, this is the pressure gauge on the driller console. You have it in this example 2000 psi. This 2000 psi, while we are off bottom, we have the pressure loss through root pipe, the pressure loss through bit, and the pressure loss through surface lines. All those three components are the same, always same, and the same flow rate. And while you are off bottom, you have the no load pressure loss through the motor, meaning the bit is off bottom, no load on the motor. So the weight of bit is 0. The bit speed is for free rotating, and let's consider it as a maximum speed at this condition. You have 0 torque from the motor, therefore you have 0 differential pressure while you're off bottom. When you're coming down and tacking on bottom, this is your on bottom here with some certain weight on it. Now you start having some weight on it. You still have the same pressure loss through root pipe, pressure loss through bit, and pressure loss through surface lines. What you have now over the motor is the no load pressure loss through the motor as when you were off bottom, and now you're on bottom, you have operational differential pressure loss through the rotor, and this operational differential pressure will produce the torque on the motor to drill. So now the bit is not rotating at its maximum speed anymore because it is restricted by the torque, and you have differential pressure on the mud motor, which is defined as now the pressure on bottom minus the pressure off bottom. In this example here, the pressure on bottom now increase up to 2500 psi. You minus 2000 psi, you have 500 psi difference. In this case, 500 differential pressure psi here. Alright, and when you run the motor at a very high differential pressure, sometimes you see that the pressure stalls. You have high torque, you have high pressure indicator, high pressure shooting up on the surface. In this example, the pressure shoots up until 3000 psi. So from 3000 back down to 2000, you have 1000 psi differential here, and it may stall your mud motor. Alright, when you have mud motor stall often, frequently, you may destroy the motor, you may cause damage to the stator, rotor, stator rubber, and you may shorten the service life of the motor. You may not achieve the whole session within one motor run. Furthermore, let us examine some other key information and key data about a mud motor. In this example here, we examine the 9.5-inch Ultra SL mud motor. This is a model mud motor from Baker Hughes. Similar to other tools, mud motor has a range of operational flow rate. This motor has an operational flow rate in range 530 to 1200 GPM. So we need to stay in this range to operate this motor. And this motor has the speed, the ratio from speed to flow rate is 0.15 revolution per gallon. So you want to work out how much the bit is rotating downhole, you take this 0.15 revolution per gallon times the flow rate, the GPM that you are pumping through the motor. And next is the operational limits of differential pressure. In this example here, the motor is equipped with two types of stator rubber. This is the high temperature elastomer. It has the range of differential pressure from 870 to 1400 psi. And when you change to the Duramax elastomer rubber on the stator, you have the range higher from 1300 psi to 1750 psi. The key thing is stay tuned within these ranges and try not to run the motor at the high end of the differential pressure. You're running it at the high end of the differential pressure, you have higher chance of stalling the mud motor, and that will in turn cause higher chance for the motor to fail. And you may not, let's say, as I said before, you may not achieve the whole session within one run of mud motor. Secondly is how fast can you rotate the drill string, or we call it surface RPM. It is restricted by the IKO angle setting, the hole size, and the size of the motor, of course. And the third important thing is the stabilization configuration of the mud motor. A mud motor has three stabilization configuration: slick configuration, partial stabilization, and full stabilization. Over here, for the simplicity, we're not getting into detail of what is the definition of slick and how partial stabilization, and how is full stabilization. Those are very detailed and specific for directional drillers. For you guys, you don't need to go into that detail. What you need to know is look at the table and understand in one hole size, for example 12 inch, with this 9.5-inch motor in the slick BHA motor at 1.6 IKO setting here, you can rotate at 60 RPM. But for the same thing, but in full stabilization, and you can rotate at only 30 RPM on the surface. So there is a tremendous reduction in string RPM in this example here. And as we said before, directional drilling with a mud motor is a combination of sliding and rotating along a plane well path. This line here is a smooth and curved line here is the plane well path, and just for the sake of simplicity, we make it simple that the red line is the rotated section and the purple line here is the sliding section. So you look at this combination, you see the profile of the well bore geometry is not smooth. It's a section connected to another section, and it may go up, it may go down, it may go left, it may go right, it may be oversized at this section, and it may be gauge size at this section. So finally, when you drill a hole with a mud motor, you may end up having a well bore geometry in hourglasses like this, or in spiral riffling shape like this. Therefore, you drill with a mud motor, you require lots of rimming and back rimming to smoothen the well bore, to smoothen some potential high local dogleg severity. You know, high local dogleg severity are extremely dangerous for hole cleaning, and in turns it may cause stuck pipe because of hole cleaning or because of key seating. But the upside of directional drilling with a mud motor is cost effective, and in some certain application where the kick-up angle is below 3 to 5 degree inclination, and you have to use mud motor because rotary steerable cannot detect hole inclination at very low inclination in range from 3 to 5 or even below that. And those are major things about directional drilling with a mud motor. So many thanks for your watching, and I hope that you enjoy and get some useful information out of this video. And if you have any questions or comments, please direct them to my personal email address at lich.tran01@yahoo.com.sg. And remember not to forget checking out to check out the website www.drilling-academy.com. There is plenty of other upstream oil and gas drilling articles and posts available in there. Thank you and see you soon in next post.